And then just for table 1.2 is going to be the properties of the section that what shows on this table there. You may figure out we've got the columns one is going to be the type of sections in a way. We have a circle shaft, things like that. And then the second column is going to be polar moments of inertia J is there. And then the shear stress is going to be the tau maximum. It's going to be experiencing right there at the surface, of course. So all of shear stress yield maximum at surface most of the time, things like that too. So therefore, number one right there is going to be circle, and number two is going to be hollow circle. It's going to be have a J corresponding there in the second column, and third is going to be the tau max is going to be there right there at the surface there in the square. Okay, square shaft, things like that, and square hollow right there. Okay, and then rectangle, and then rectangle with a hollow inside, and then number seven is going to be hexagonal. That's what we've got there with the J and the tau max experiencing right there at the surface of the shaft, respectively. And then we have an example right there that what I would like to show you up there. It said here, a shaft transmitted to 8 powers of 10 kilowatts at the constant speed of 1,500, I'm sorry, 1,750 RPM. Is made of 1030 CD steel and then determine the shaft diameter by using the yield strength and the safety factor n sub y equal to 2 when the design shaft is A is solid on the way and B is hollow by using D sub over D sub I is 2. Okay, so therefore, it's given by the problem set 1030 CD steel. So therefore, based on appendix 1.1, we got a sigma y of 440. So therefore, we got 440 newton per millimeter squares. And then since this problem set is going to be tau sub y is all the way, so therefore we find automatically tau sub y is equal to 0.6 sigma y due to the simple stress relationship, of course. And then tau design is given by some set that n sub y is equal to 2. So that's why the tau design is equal to 132 respectively. It's equal for the solid shaft. Number A there is given by the problem set, right? 10 kilowatts and n is 1,750 and 10 kilowatts is times by 1,000 there. We find automatically the torque is in there is newton meter. And then based on table 1.2, we found the tau is going to be equal to 16t over pi d cubed. And we make substitution there. We got one unknown left there. We got the diameters of 12.8 millimeter, respectively. That's the answer. And then for the questions number B there, we found the hollow shaft. We just plug in the tau there as an equation. We solve only one single parameters there is going to be d sub o. So therefore, Skipman problem said that d sub o over d sub I is equal to 2 by the problem set there. So therefore, we switch everything to be d sub o. So therefore, we plug it in there. So therefore, we've got the d sub o gonna be the answer of 13.1 respectively. So therefore, we got the one things left over is d sub I. So this answer is going to be quite a significant number. You may compare the answer to each other. See, d sub O of H is going to be 12.8 and 13.1. They're very close to each other. See, nowadays, for the new technology, we can be able to find the hollow shaft easily, but during my time, it's difficult to find a hollow shaft. But your time today, technology is ready to grab up the D sub O and D sub I or the hollow shaft easily. They're just gonna reduce a lot of weight, things like that for the shaft. This is gonna be a second chance for you anyway. Okay. And then example 1.5 is another things that what you guys should think about it. Have a look at it by yourself. Okay, another example. Okay, let's go for another types of stress that what we call bending stress, of course. Okay, bending stress due to pure bending. What does it mean by pure bending? Pure bending is mean only bending loadings applied on it. So therefore, if we just got only pure bending, we gonna have the sigma b equal to m times c over I. It's gonna be right there. For the figure 1.8 there, we have a beam, simple support beam, we have a left support and right support respectively. We have a force of F that what we call transverse loading. This force is mean this force acting perpendicular to the axis of the beam. So therefore we got transverse loading anyway. So therefore this beam just tend to be bent like a curve, things like that all the way when we have a neutral axis. I trying to make a drawing look like that. Neutron X is not exactly right there at the middle of the cross-sectional area. It's sometimes whatever is not necessary to be right there at the center. So therefore, neutral axis means the stress is going to be zero there at this axis. So therefore, this is the things that what you show you up there. So therefore, this type of thing, see that what I show you there is that since the cross-sectional beam may have different shape, table 1.3 show you some properties of the section. Okay, so there I show you there in the table 1.3 already, and then on the appendix 2. Okay, so could you please have a look at it? I have done a shear bending moment diagram, okay, of many types of loading, okay, acting on the beam, many types of the beam, simple support beam, cantilever beams, and many types of the beam acting on the load, only single load and a double load, things like that on the beam, things like that, okay. You may figure out making use of it. And then another things that what my experiencing, okay, this type our experiencing not only the bending stress, we experiencing the shear stress induced also with the beam, okay, within the beam. We experiencing it the round if the beam have a shape of round section like that. Okay, we experiencing a tau max right there at the center. Okay, this tau max is equal to 4v over 3a, and we're gonna be yield minimum at the surface. If you compare it to the beam there, okay, you're gonna have maximum, okay, sigma, okay, right there at the surface, and then minimum at the neutral axis. Okay, it's this opposite sign here. Okay, it's gonna be minimum there at the neutral axis. Okay, maximum at the neutral axis of the tau max, and the minimum it could be zero or minimum anyway at the surface. It's going to be on the opposite sense anyway. It's going to be in the opposite sense anyway. Okay, so and when the cross section is going to be in terms of rectangle, okay, it's going to be 3v over 2a maximum right there at the center of the axis, and it's going to be zero at the surface. Okay, it's going to be for V's over A for the average, of course. Okay, so this kind of thing, please take in mind. Okay, I make a conclusion here, the maximum of the shear. So therefore, in conclusion, okay, so therefore, for the acting of the external force of the transverse loading, we just experiencing two forces anyway. Okay, one is going to be sigma, second is going to be the tau at the same time. So therefore, this type of thing happen mostly in the beam. Okay. So therefore, let's see the example quickly. Example 1.6. A simple support beam with a rectangular cross-section area is subject to a towards loading of F equal to 40 kilonewton at the middle of the span. Given that the beam is made of steel having the yield strength of sigma y equal to 552 megapascal respectively, and the Young modulus of E207 gigapascal determine A, maximum bending loading, maximum bending stress of B, and C is safety factor, and D, maximum deflections of the beam, E is maximum shearing space, respectively. Okay, let's see the figure there. Okay, we have F right there at the center. We have a simple support beams upon the left, and on the right, the beam has rectangle with the B of 30 at just 100. So look up in the appendix number 2 there. We have a simple support beam, and then we have a look right there at the appendix number 2. We automatically find the bending moment equation of equal to x times f times x over 2, and then we plug it in, okay, for the maximum. So see, based on appendix number 2, it's u maximum at x equal to f, x equal to L over 2 there at the middle of the span. So therefore, I make substitution x equal to L over 2 right there. So therefore, I find the maximum moment is equal to F times L over 2. So I find the result is going to be 10 Newton meter, things like that. Okay, and then the maximum bending stress. Okay, I find the I from the table 1.3 there is equal to B times H cubed over 12. I just make substitution there for the Krippmann problem set, and then M times C. I make the substitution there also. I got a sigma B there. That's the answer. So automatically C is going to say the factor is equal to sigma Y over sigma B. I find it automatically 2.76. Okay, and based on appendix number 2 there, I find the Y max there. I put it up there, and then I make a substitution to the corresponding number. I got the answer there, and then also the question is, I got the appendix 2, the maximum shear force. I found it. V is equal to R1 equal to F over 2 respectively. Constants all the way from the left to the right. Okay, it's going to be 20. So therefore, the tau max is going to be equal to 3V over 2A, because that's why this is a rectangle, right? It's going to be right there at the center of the beam. Okay, so therefore this is the answer of the question E, respectively. Okay, so this is the things that what based on the example of the bucking the beams anyway. Okay, so next is gonna be the last thing that what we're gonna go for the bucking stress. Okay, bucking. What does this mean by the bucking anyway? Marking is gonna be the things that what typically the machine component gonna bend on the side, okay, with a long column, things like that, okay. So let me read it out for you guys then, okay. Bucking stresses mean a long member of machine component subject by an axial compressive loading is typically designed by using column design. Typically, when a long column subject to an axial compressive loading, the column will be buckled and then experience failure. Even the induced stress in the column is still less than the allowable stress. Therefore, the principle of the simple stress, which is sigma equal to F over, cannot be able to employ for this column design anymore. Uh-oh. So therefore, the column design should be classified as long column, intermediate column, and short and compressive member. So therefore, the things got to be judged which one is going to be number one or number two is the slender ratio then. Slender ratio is determined from L sub E over K. This is going to be the index there. So let's see L sub E first. L sub E we call it effective length. The effective length is depend on the configuration, okay? But configuration for the types of column is going to be in figure A, B, C, or D, respectively. In figure A, see, we have a column, look like that, okay? The first end, okay, we just, okay, fix it, okay, and then we have a joint there, okay, and then another joint there. We have another end, we just apply the force on it. We allow them to move in the up and down position, but not on the side, okay, so the L sub E equal to L respectively. And then in figure B, okay, we fix down under one end, the other end, okay, we just let them free all the way. The L sub E equal to 2L right there, okay, and then in figure C, if we fix both ends, okay, both ends. So therefore, the L sub E equal to 0.5L. This is most of the machine parts that what we typically do on it. And D is going to be another type of machine parts. We fix one end, another end we just allow them to just move only one direction. Okay, another one where we just fix it. Okay, we just fix it. Okay, we just have the L sub E equal to 0.7 L. This is the typical types of the configuration of L sub E, or the feelings, of course, based on the configuration. So another one is K, is radius of gyration. Okay, radius of gyration is based on two factors, I over A. Okay, I is going to be area of moment of inertia. It's considered in here using the lower value of I sub I bar anyway. For example, use of I sub y for this configuration. Okay, let's see this configuration. B is small and H is high. So B is small and H is high. So therefore I sub x and I sub y, of course, I sub x is equal to BH cubed over 12. I sub y equal to HB, right? HB cubed over 12. Things like that. So of course, right? I sub y, right? Gonna be very small, right? Very small. So therefore, we're gonna use I sub y for this configuration, for the calculation. So, or we just might say that, okay, it's gonna do the buckle in the y direction. Okay. So therefore, the cross-sectional area is going to be A there. Okay. And then therefore, another one is going to be critical loading, F sub CR, and then the critical stress is going to sigma sub CR, respectively. And then we're going to have the equation of Euler formula. And then we're going to make some judgments for the long column by using the slender ratio. If L sub E over K is greater than C sub C, we're going to apply for long column. If the L sub E over K is less than C sub C, we're going to determine it as a short compressive member. We're going to apply for the Johnson formula, respectively, okay, by using the formula like that. Okay, so otherwise C sub C, then C sub C is defined from the characteristic, okay, of this 2 pi square or time E over sigma y, because that's why E and sigma y are the constant term that's going to be the characteristics of the member of the machine members, things like that. Okay, so therefore, okay, this is the graph that show you there. Okay, the regions here is gonna be chart member. Okay, the member just beyond B point is gonna be long member. We're gonna apply for the Euler. For rather than B, here is gonna be Johnson. Okay, if we apply for the long member, the graph is gonna be divergence, things like that. Okay, you got to be careful here. Sometimes, see, if we're gonna have a short member there, we can be able to apply for Johnson gonna be equal to, okay, Johnson we can write down here is gonna be approximately the same as F over A, of course, for the Johnson. Okay, sigma sub CR is gonna be estimated to be F over A. Sometime it's very equal to each other. Okay. All right. So this is gonna be the theory gonna be about it already, and then okay. So let's go for uh, the thing that what we left over. Okay. Okay. What we left over there is gonna be uh, let's see. Let's see there. One example there, 1.8. You may have a look at it by yourself. Okay, 1 point there, 1.8 is gonna be some kind of example. Example 1.9. Okay, this is gonna be a binary. Join there. Very good example. Have a look at it by yourself. Okay, and then example 1.10. I used to put this one maybe like 5 years ago. Okay. I put this one, okay, as an example, as a exam, okay, as an exam, but 5 years ago anyway. So therefore, this is hydraulics beam, things like that, okay. That's what I put it on. I asked for the diameters of the lot here and the thickness of the wall of the cylinder. May have a look at it, okay. So it's pretty straightforward to have a look at it, okay. And then 1.11, another exam, okay, that what I put it up for you as an example, okay, for me 2 years ago, okay. You may have look at it by yourself, okay. This one, okay, this the hydraulics, this one, I'm sorry, this is going to be the arms, okay, crank arm, things like that, okay. You may have a look at it, okay. Okay, it's gonna be very straightforward anyway. Okay, so you may have a look at it. Okay, and then okay, so have a look at the prompt set. Okay, number one, you better practice by yourself. Don't submit to me. Okay. Number two, practice by yourself. Number three, practice by yourself. Number four, practice by yourself. Number five, please, okay, just do it and submit to me, okay? As a homework and submit to me. Number five there, okay? And number seven, please, okay? Five and seven as an assignment for me, okay? Just submit it to me as homework, okay, everybody, please, okay? So that is it for the chapter one. Okay, I would like to make a lecture. Okay, for all of you guys here. Okay, have fun on it. So trying to solve the problem. I promise to you to solve every single problem that what I assign for you. Anyway. Okay. So okay, I will stop my lecture for today anyway.